Greetings. Welcome to the AP Physics Summer Assignment. This part is on unit conversions, and if this is the first video you're watching in this series, just letting you know that we're going to start with some example problems, and essentially this worksheet that you have in front of you is going to be example problems, and there are total of 7 example problems, one of which is broken into 2 parts, so if you want to call that 8 example problems, that's fine. Because these are just sample problems, these are designed to show you how to do the real problems, this particular worksheet does not need to be turned in. However, there is a worksheet with some very similar problems that does need to be turned in. The main skill that I'm trying to teach you guys with these sample problems is something called the factor label method. Now, if you took a chemistry class, which it's almost impossible to get to AP Physics without taking a chemistry class, but if you took chemistry, so almost all of you took chemistry, and in chemistry you had stoichiometry. Stoichiometry is an example of the factor label method. You're going to start with a quantity, and then you're going to multiply by a bunch of conversion factors, which have equivalent values on the top and the bottom. So that is really essential, that you have equivalent values on the top and bottom. But instead of using this to solve just chemistry problems, we're going to use this to solve some more complicated unit conversion problems. In the past, you probably got unit conversion problems like number 2. The wavelength of a typical infrared light is 0.940 micrometers. Convert this into centimeters, right? It's a very simple unit with just one unit, no divisions, no squarings, no cubings, none of that. And you have to convert it to another unit, and you do that by moving the decimal point. Now, for simple examples like this, moving the decimal point approach does work. But as soon as you get something more complicated like this, where you have the speed of sound in salt water is 1,560 meters per second. Now you've got meters on top and seconds on the bottom. This is actually a fraction. And you have to convert that into kilometers per hour. Then the moving the decimal point doesn't work. It doesn't even work as well. It just doesn't work, period. Now, as a side note, there are a small number of unit conversions that you are expected to memorize. So let's put those on the side here. Okay, so things you need to memorize include the prefixes micro, which is this thing that looks like a U. It's actually the Greek letter mu, and that means 10 to the negative 6th, or 1/1,000,000th. Milli, prefix lowercase m, that is 10 to the negative 3rd. Centi, abbreviated with a lowercase c, that's 10 to the negative 2nd. And kilo, which is abbreviated with a lowercase k, which is 10 to the positive 3rd. And the other documents that accompany this are, they go into a little bit more detail on examples of what do we mean by 10 to the negative 6. So for example, a micrometer is 10 to the negative 6th regular, 1 times 10 to the negative 6th of a regular meter. Or 1 micrometer is 10 to the negative 6th regular meters. Or 1 kilometer is 10 to the 3rd regular meters. Also be aware that something that you will really need to know for physics is the conversions between time, which are not based on powers of 10. They're based on multiples of 60. So there are you can say that 60 seconds is equal to 1 minute, and 60 minutes is equal to 1 hour, and therefore 60 times 60 gives you 3,600, not 360. 3,600 seconds is equal to 1 hour. Now, you notice I started writing these as equations. Stuff on one side, equal sign. Stuff on the other side, that's an equation. And when you take an equation, your algebra classes should have taught you, certainly did teach you, is that what you do to one side of an equation, you can do to the other side of the equation. So looking at this 3,600 seconds is equal to 1 hour, we can divide both sides by 1 hour, and then this equation becomes 3,600 seconds over 1 hour equals 1, a unitless 1. And then the other thing you can do is you can divide both sides by 3,600 seconds. You go back to here, backtrack to here, and divide both sides by 3,600 seconds, and you get the alternative conversion factor. I almost said alternative fact, but in modern politics that has a different meaning, of 1 hour on top and 3,600 seconds on the bottom is also equal to 1. So these are two different ways, two different fractions which have equivalent quantities on top and bottom, and that makes it equal to 1. And remember that in multiplication, multiplying by a unitless 1 does not change the value of the quantity that you're manipulating. And that's overall the goal of unit conversions, is to change the units without changing the fundamental value that you're measuring. Oh, by the way, before it becomes an elephant in the room, you may notice on my fingers there's some little scrapes. I did a little bit of a bare knuckle workout the other day, so that kind of injury is common when you're punching without gloves. Okay, no, the punching was not directed at any person. It was directed at inanimate objects. So getting back to the problem. Speed of sound is 1,560 meters per second. So let me switch colors here. I suppose I'll do the actual solutions in blue. All this stuff is side work here. So 1,560 meters over 1 second, right? You can rewrite this as this without changing anything. And rewriting it this way helps because you can see which units are on top, which units are on bottom, and that tells you what units you have to change. So we have to change the meters into kilometers and the seconds into hours. And just like in stoichiometry problems, we want to multiply by quantities that have the stuff we want to get rid of on the opposite side of where it is now. So if I do the meters to kilometers conversion, the conversion factor I want needs to have meters on the bottom, and ideally it'll have kilometers on the top. And we can do that based on this chart here. 10 to the third meters is equal to 1 kilometer, or 1,000 meters is equal to 1 kilometer. Again, your conversion factors should have equivalent quantities on top and bottom. And when you do this, you can check that the units will in fact cancel out. The units we don't want in our answer, that is meters, cancel out. And we're left with units we do want, which is kilometers, and we're left with that unit, in a position that we want, which is on the top of the fraction, right? We want kilometers on top, hours on the bottom. Okay, but we're not done yet. If we were to stop here, we would get some number, let's say it would be 1.56 kilometers per second, which is a real unit of speed, but the problem actually asked you for kilometers per hour. So we have to convert the seconds into hours. So we're going to do that with a second conversion factor. Oops, I said solutions are going to be in blue here, so let me switch back to blue. There we go. Yeah, fortunately blue is darker than red, so nobody saw that mistake. So we need some conversion factor that has an equivalent unit of seconds on the top and hours on the bottom. And we just made two versions of that right here. Seconds and hours in the same conversion factor, and the green one here is the only one that actually has seconds on the top and hours on the bottom. So we can write 3,600 seconds for every 1 hour. All right. Double check to make sure the units you don't want are canceling out. Okay, we got seconds on the bottom down here, seconds on the top here. That cancels out. The only units that haven't been canceled out are kilometers on the top and hours on the bottom, which is what we're going to have. So that's going to, in our answer, kilometers on top and hours on the bottom. And that's going to be what the problem asked for. And now it's just a matter of throwing everything into the calculator. Remember that this dividing by 1 and dividing by 1 doesn't change the value, etc. So we got 1,560 divided by 1, let's leave that off. Multiplied by 1, leave that off, divided by 1,000. That's important. Times 3,600 divided by 1 gives us 5,616 as our quantity. And that's going to be over 1. Or, as it's more commonly written, 5,616 kilometers per hour. Okay, so that is our answer there. That's how we got that using the factor label method. We started with the quantity we're given, we keep in mind the units that we want, and we multiply by conversion factors until the units we don't want go away, and the units we do want are all that's left. Basically the same approach, except it's actually even simpler for problem number 2, wavelength of light of infrared LED light. Wavelength of a typical infrared LED light is 0.940 micrometers. Okay, so 0.940 microns or micrometers. You could, if you prefer, put a unitless 1 on the bottom here. You don't have to. If you like, if you just kind of get in the pattern of starting with a fraction, fine. Make it a fraction by putting it over 1. But you don't have to. So we need to get rid of the micrometers. So the next thing we multiply needs to have micrometers on the bottom. And this conversion factor here tells us that there's 10 to the negative 6th regular meters in 1 micrometer, or you could flip that around and say 10 to the positive 6 micrometers is 1 meter. It's all the same. You could, but I just find positive exponents less confusing. So this is progress because the micrometers cancel out, but we end with, if we were to stop here, we would end with meters. And that's not what we want. We want centimeters. So we got to convert the meters back to centimeters. And there are 100 centimeters in 1 meter. Again, equivalent quantities on top and bottom. Okay. Now, you could get a little fancy and say that there are 10 to the 4th or 10,000 micrometers in 1 centimeter, and that would limit you to just one conversion factor. That's fine. I just find it faster and clearer to do it this way. Okay, so, but ultimately the math works out the same because you are dividing by 10 to the 4th, and let's see, this is already 10 to the negative 1st, so 10 to the negative 5th. Okay, so this is 9.40 times 10 to the negative 5th centimeters. Okay? And you could express it in conventional notation if you want. You don't have to use the scientific notation. But when I get down to that many zeros after the decimal point, I'm just in the habit of using scientific notation. Okay, now things are going to get a little bit more complicated. The volume of Lake Mead, the lake behind Hoover Dam, is 35.2 cubic kilometers. Convert this into cubic meters. Okay, now we have a unit that is cubed. And when you're dealing with exponents on your units, it is no longer good enough to just use the units. To just use the old conversion factors. Allow me to explain. So, side note here, I'm going to go off on a separate sheet of paper here. All right, so let's say we have a cube. And this cube is 1 meter wide, 1 meter tall, and 1 meter deep. In other words, this is 1 cubic meter. Okay? Well, 1 meter is the same thing as 100 centimeters. And so if we were to calculate the volume in centimeters, it's going to be the width, so it's 100 centimeters, times the height, which is 100 centimeters, times the depth, which is 100 centimeters. And so the volume of this cube expressed in centimeters is going to be 100 times 100 times 100, which is 1,000,000, or 10 to the 6th cubic centimeters, because we've done centimeters times centimeters times centimeters, which gives you cubic centimeters. In general, when you're multiplying and dividing, whatever you do to the numbers, you also do to the units. So we cubed 100, we also cubed the centimeters. All right. But this is also it's still true that this is a 1 cubic meter object. So the volume in cubic meters is 1 cubic meter. The volume in cubic centimeters is 10 to the 6th cubic centimeters. So you can no longer say that 1 cubic meter is 100 cubic centimeters. No, the relationship gets a lot more complicated. Until you realize that, hey, wait a minute, if what I do to the numbers I also do to the units, if that is true, which it is, then there's a pretty straightforward way to do this conversion. If you have 35.2 cubic kilometers, and you know that 1 kilometer is 1,000 meters, again, units you want to get rid of on the bottom, units you want to keep on the top. Okay? Well, this is like having x cubed in a numerator and x to the first in a denominator. It cancels out, or partially cancels out, to give you x squared. But conversion factors are really just fancy ways of writing 1, right? All of these conversion factors have the same quantity on the top and the bottom. And so they're essentially just 1. And multiplying by 1, if you can multiply by 1, you can multiply 1 and then multiply by 1 again. You can multiply by 1 and then multiply by 1 and then multiply by 1 and then multiply by 1. So what I'm getting at is you can just use the conversion factor 3 times. And then these 3 kilometers in the denominator cancel out with the cubic kilometer in the numerator, just in the same way that x cubed on top of a fraction and x times x times x on the bottom of the fraction would cancel out. And then what we're left with is meters times meters times meters. In other words, we're left with cubic meters. So this is 35.2 times 10 to the, ninth cubic meters, but this is not good scientific notation. Scientific notation should have one and only one digit to the left of the decimal point, so we're going to move the decimal point this way once, and so in other words, we're going to make this 10 times smaller, which means we make the other part of the fraction 10 times bigger in order to preserve the value. So this is 3.52 times 10 to the 10th cubic meters. Now, if you like writing out lots of things in response to your AP Physics problems, go ahead and write this. The alternative would be just to say 35.2 cubic kilometers times 1,000 meters over 1 kilometer, and then you take that conversion factor, slap some parentheses around it, and then cube it. Okay? That is really the exact same thing as what we did here. In other words, you got cubic units, fine. You use cubic conversion factors. Okay, so these are just two different ways of solving the same problem. In fact, they're minor variations on the same way. All right, sticking with the theme of Hoover Dam, the generators in Hoover Dam can produce energy at a rate of 2.080 times 10 to the 9th joules per second. Convert this into kilojoules per year. Okay. This is going to get a little annoying for two reasons. Reason number one is that you're going to have to convert seconds into years, and that's going to involve a few different conversion factors. And the second thing is that it will vary a little bit depending on how accurate you want to be for your definition of 1 year. Do you call it 365 days? Do you call it 365.25 days? Whatever. I will err a little on the more accurate side for this case. Sorry, I'm going to pause the video for just a second. Okay, with that brief interruption aside, the generators in Hoover Dam produce energy at a rate of 2.080 times 10 to the 9th joules for every 1 second, right? Units on the bottom means you write the units on the bottom with a 1 next to it. And now we have to convert joules to kilojoules. Okay, that's a straightforward kilo units to base units. Okay, so if we say we want, well, if we got joules on the top and we want to get rid of that, so we want regular joules on the bottom and we want kilojoules on the top, and 1 big unit is the same thing as 1,000 smaller units. Okay. So that's going to be the conversion rate we use, the conversion factor we use to get from regular joules to kilojoules. Now, the time conversion is going to be a little more complicated. We can save a step or two by using one of these. And if you look here, you got seconds on the bottom, which means that in order to get rid of seconds, you need something that's got seconds on the top and hours on the bottom. And that would be 3,600 seconds over 1 hour. So if we do 3,600 seconds over 1 hour, that's good in that we will get hours, but we want years. So there are 24 hours in 1 day and 365.25 days in 1 year. That extra 0.25 day, that's why we got leap years. Okay, so double check before you throw things into your calculator to make sure your units cancel out. Joules here, joules there. Seconds here, seconds there, hours there, hours there, days there, days there. Now, if you have seen the movie or the musical Rent, you will know from the song how many seconds are in 1 day. I'm not a big musicals guy. However, this is one of those cases where you could be, it would be a little more advantageous. You could use one single conversion factor to go from seconds into years. I don't recall the actual number, hence the reason I use this more complicated series, well, not more complicated to me, but this longer series of conversion factors. Okay, time to do the actual math. Now that we know that that the units cancel out, we got kilojoules on top, we got years on bottom, everything else cancels out, so we're good. We got 2.080 times 10 to the 9th divided by 1,000 times 3600 times 24 times 365.25. Okay, double check to make sure that what we're doing is multiplying when we should multiply, dividing when we should divide. Okay. And we get a really big number. That's times 10 to the 13th. So this is 6.56. Let's see, we got 4 sig figs there. By the way, conversion factors, at least within the metric system, they are exact numbers, and hence they have infinite number of sig figs. There are exactly 24 hours in one day. There are exactly 3,600 seconds in 1 hour. So you don't need to count sig figs on your conversion factors. All right, so this is 6.564 times 10 to the 13th kilojoules per year. Oops, I went off a little bit. Let me zoom out a bit. Boop. Okay. Okay. Los Angeles Aqueduct can deliver water at a rate of 22.9 cubic meters per second. Convert this into cubic kilometers per hour. Okay, so now we've got all the complication of the volume of Lake Mead problem, where we have cubic units and we have units on the bottom as well. So we have 22.9 cubic meters in 1 second. Okay, multiply this by 1,000 meters for every 1 kilometer, but we got cubic meters, so, oops, you did not see that too. Okay, so you take your kilometers to meters conversion factor and you cube it in order to make it appropriate for cubic units. Then we need to convert the seconds into hours. Well, I already worked that out over here. Let's see, we want seconds on the top, so that's going to be multiplied by 3,600 seconds for every 1 hour. And this will take care of the conversion that we need, and we'll end up with a very small number. Okay, so be careful when implementing parentheses on your calculator. So we got 22.9, no parentheses there. And then we have times parentheses 1 divided by 1,000, close parentheses, and then raise that to the 3rd power. Okay, you want it to do the divide 1 over 1,000 first, and then you want that to cube, that and only that to cube. Just the stuff between my 2 index fingers right now, that's all that gets cubed. That's all that gets cubed. Okay? And then you multiply by 3,600. No cubing on that. And we get a pretty tiny number. Yeah, that's the right order of magnitude. Okay. So that's 8.24. We got 3 sig figs. Yeah, 8.24 times 10 to the negative 5th. And this is going to be in cubic kilometers for every 1 hour. Oh, by the way, in AP Physics, please be sure to put a box around your final answer, because we'll be doing a lot of calculations in this class, and sometimes it'll be hard to figure out which of the myriad of numbers is your actual answer. All right, a small solar panel can generate electricity at a rate of 0.00977 joules per square centimeter second. In other words, for every square centimeter of solar panel, and for every second, I get 0.00977 joules. Convert this into kilojoules per square meter second. Okay, we're getting increasingly complicated stuff on the bottom. of the fraction. And by the way, like I said, all of you have done chemistry, so you've all seen gas laws. You remember how complicated the units were in gas laws? Well, physics gets the same kind of treatment. Okay, here we go. 0.00977 joules per cm squared dot s. That dot means that the centimeters squared and the seconds are multiplied together in the denominator of this fraction. And if you want, you could make this a fraction where you have 1 square centimeter second on the bottom. It's not 1 square centimeter per second, it's 1 square centimeter second. Okay, but really it's the same logic that we've been using all along. Convert joules to kilojoules. So we need to get rid of joules that are currently on top, so we need the 1,000 joules on the bottom and the 1 kilojoule on the top. And then we need to convert the centimeters into meters, so that's going to be 100 centimeters for every 1 meter. And since this is squared, we're going to square the conversion rate. In other words, we're not going to multiply by 100, we're going to multiply by 10,000. And then we convert the seconds into nothing. We don't need to convert the seconds. Okay? You don't always need to convert a unit just because it's a unit conversion problem. All right. 0.0097. You can't read that. 0.00. Yeah, let's do this so you can read everything. 0.0097 divided by 1,000 times 100 squared is 0.097 kilojoules per square meter second. All right. The Sierra Sun Tower power plant, located just outside of Lancaster, California, can generate electricity at a rate of up to 62.5 joules per meter squared second. Convert this into kilojoules per kilometer squared hour. By the way, this particular design of a solar power plant acts kind of like a gigantic magnifying glass. It's called concentrated solar, and it takes a bunch of mirrors and uses that like a giant magnifying glass to shine a bunch of light into a single point. And then at that point, you run water through it to get steam, use the steam to generate electricity. Okay, but it implies that, or at least the implication is that if we make it bigger in area, in other words, if we have more square meters in our giant field of mirrors, then we can generate more joules of electricity in the same amount of time. Or if we have more time, we can generate more joules of electricity with the same area. Nevertheless, we got 62.5 joules for every 1 square meter second. And so we need to convert the joules to kilojoules. So that's going to be 1 kilojoule for every 1,000 joules. And then we're going to convert the meters squared into kilometers. That's not a negative sign. That's just my pen touching the paper at the wrong time. Okay, so we got to square that. So that 1,000 is going to become a million. And then we got to convert the seconds in the denominator into hours. So again, way back up here, seconds on top, hours on the bottom. That's 3,600 seconds for every 1 hour. Okay. So throw it all in your calculator. 62.5 divided by 1, which really doesn't count, divided by 1,000, which does count, times 1,000 squared, times 3,600. That gives you a number that's on the upper limit of what we can express without scientific notation. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 2.25 times 10 to the 8th. And what the heck were the units we were trying to go for? Kilojoules per square kilometer hour. Okay. Last but not least, last example problem here. Given the rate of electricity generation above, how many kilojoules per second, notice that we got rid of the area quantity, could an 8 million square meter power plant generate? Okay, the underlying assumption here is one of direct proportionality. In other words, if you have twice the area, you generate twice as much energy, which, as I mentioned, given the design of this the solar power plant, is not too bad of an assumption. Certainly good enough for first pass. Of course, there's going to be more detailed engineering in actually making one of these things and more importantly determining whether or not you can make money off of it. Nevertheless, for first pass of calculations, not bad. Expressing the power per unit area energy per unit area per unit time means that if you have a 1 square meter power plant, you generate 62.5 joules per second. If you have a 2 square meter power plant, you generate twice as much. So that would be, 125 joules per second. Okay? So if you have 8 million, then we got to take this quantity and multiply it by 8 million. So we start with 62.5 joules for every 1 meter squared second. And then we're going to multiply by the 8 million square meters. Okay. And the meters here, square meters here is going to cancel out with the square meters there. And then we're going to be left with joules per second, which is not the actual units we want. We want kilojoules per second. So we need to convert the joules into kilojoules. So that's going to be 1,000 joules on the bottom and 1 kilojoule on the top. And when we do that, the joule here cancels out with the joule there, and we're left with kilojoules on top, seconds on the bottom. That's the units we want. Things are hunky-dory so far. All right, and if you want to get fancy with the math, you can do some cross cancellation. So this 1,000 cancels out these last 3 zeros, and so you could save yourself a couple seconds of time by saying you got 62.5 times, 8,000. Okay, so that would be 500,000. Or you could do the whole calculation if that doesn't come particularly naturally to you. 62.5 times 8 million divided by 1,000. And presto, math works. You get the same answer. So we got 500,000 kilojoules per second. And if you're a stickler for sig figs, you started with 3 sig figs here, the 6, 2, and the 5. It's not really clear how many sig figs you've got. So this is admittedly ambiguous number when it comes to sig figs. And then this, the kilojoules to joules conversion rate is exact, so there's infinite sig figs here. So it's not entirely clear. You could round it off to as few as, if you want to be the most conservative, it'd be 5 times 10 to the, 3, 4, 5, 10 to the 5th kilojoules. I said kilojoules per second. 5 times 10 to the 5th kilojoules per second. Okay? All right, so that's how to solve these unit conversion problems using the factor label method. I hope that this gave you enough knowledge that you can in turn tackle the actual worksheet that you need to do that has different problems on it, and that will be due on the first full day of classes.